Okay. Hello, everyone. Sorry, I have a cold. I'll try to stay here. I moved my mask because I need to talk and breathe. It's my daughter's fault. She was traveling. She came home with a cold, so now I have it. Okay. All right. So let's do a quick recap of what we talked about last time. All right. Is nutrition labeling required for all food? Yes, Haley.
Not all the ones.
Not all, but most. Can anyone give me an example of a food that, let's see. Let's go with Razi.
Fresh veggie at a farmer's market or something?
Yes, very good. Gray, what did you want to say? He took it? He took what you wanted to say?
One of them, I was gonna say fruit.
Okay, that's good too. That's good too. Tyler, what did you want to say?
I was gonna say like a beer.
No, there will be a nutrition label on beer. But it's okay, you still get your participation point. It is, you'll see it on it, yeah. Huh, Rob?
Shell eggs.
Shelled eggs, raw meat, like a little package within a big package. So there are exemptions, basically. What agencies regulate nutrition labeling? Say your name again. Graham, yeah, I don't have my cheat sheet next to me. Okay, Graham. Huh? FDA. And Molly. FSIS for eggs, poultry, and one other thing. Okay, good. All right. Food Safety and Inspection Services, that's what FSIS is. Okay. Of the USDA. What type of analytical methods are required to obtain the values listed on the nutrition label? That's a very common question. Sometimes I ask in a quiz or a midterm or a final. When I say a type, it's like a category. It's not a specific test that I'm asking for, Kendall. Official method. Yes, that's what I'm looking for. Official methods that has been validated, primary methods that we use to calibrate, secondary methods. Yes. We will learn a lot about all different official methods and also secondary methods in each of the following chapters. What are new changes in the nutrition label? Go ahead, Kristen. Yes, look at the calories. They want you to look at the calories really well. Okay, calories. Not Rachel. So no, go ahead, say your name. Huh? Alicia. Okay. Yeah, so they removed A and C, and what vitamin do you remember now? Vitamin D. Okay, Razi.
They split between like total sugars and added sugars.
Absolutely. Now we have an added sugar that is not there. Graham. No. Yeah. Calories from fat. Jordan. They added potassium. Look at you guys. Very good. Even if you're looking back at your notes, that's part of studying. So well done. All right. When can you claim calorie free? With the amount of calories less than that amount you can claim. Go ahead, Sierra. Huh? Less than 5 calories you can claim as calorie free. Well done. Okay, is the label in compliance when an added nutrient level is 80% of what is listed on the label? Is it in compliance, Sophie?
No, it's not. Absolutely.
Exactly. When you add a nutrient, it has, when somebody audit and take a sample, it has to be 100% or higher of what you say on the label. Endogenous, like part of the food, it can be 80% or higher. Okay. Very good. There we go. We studied. Yes, Rob?
For foods that are fortified and have a whole slew of added nutrients.
Yeah.
When do they test them?
Well, first of all, each company is required to have official method of analysis to claim the value. And if they're fortified or supplemented, they have to, put the either 100% or higher value on the label. Now, if they get audited randomly, anybody comes in and take a sample and measure, it has to meet what they say on the label. Yeah, but oftentimes you don't analyze the food for nutrition label every time you produce a lot, unless you make a change. Okay. Or any questions? All right, before we continue, I have an announcement to make for the lab. We had issues with the software, and I'm so sorry for that. The owner of the software messed up a few things, including number of licenses they gave us. So today's lab, several of you were not able to get into the program. And Monday we had delays because of this inconsistency that we're getting because of the program glitches. So we collectively decided to give you 2 extra days to submit the report. So Monday lab, your report will be due next Wednesday, and Wednesday lab, your report will be due next Friday by midnight. I promise once you sit down and you have all your data and all your labels, the report will not take you a long time. But we wanted to give you those additional dates so you make sure you get all of your labels printed and everything, or downloaded, whatever it is. Okay, if you have any difficulty, any special request, please reach out to us, all of us, me included, and the teams. Okay. So this is a common mix-up by students when we say nutrient content claim versus health claim. They're 2 different things. When I ask you on an exam about nutrient claim, I don't mean health claim. I don't mean health claim like calcium and osteoporosis. This is a health claim. You're linking a nutrient to a health issue. So nutrient claim is when I'm talking about the components, like when you say low fat or a good source of protein. So we're talking about a nutrient and we're giving a claim, whether it's low or good source or a high source. So there are many words and terms for nutrient levels. So free, low, lean, light, reduced, less, good source, etc. And for you or for a company to put on the label a nutrient claim, it has to follow the regulation for claiming free or low or good source of. Okay, so that's nutrient content claim. Okay, separate from health claims. Okay, so health claims, again, calcium osteoporosis, sodium and hypertension, fiber and dietary fiber and cancer. These are health claims. Nutrient claim is, I keep those tables here in the slides, although they're no longer in your chapter. The last time they appeared in the book was for edition 4. It was a decision of the author not to include them anymore in the chapter, which I tried to argue, but I failed. But I want them as an information. It's just FYI, you need to know this. You don't have to memorize. You just need to know that if it is free for calories, less than 5 calories. If it is low, it means 40 calories or less per reference amount. So the reference amount is 50 grams, then it would be whatever the calories for that 50 grams are, it would be 40 calories less. Reduced. I don't know why this box here is in the way. Okay. At least 25% fewer calorie per reference. There's always a reference, and you find this in the Code of Federal Regulation. So that's for calories, and then you will have for other for nutrients like total fat, what would be considered free, low, reduced, and then for the rest, saturated fat, cholesterol, sodium, and then sugars. So, I mean, of course, I don't ask you or expect you to know this, but this is good FYI for you. That's why I keep it in my slide, although it's no longer in the book. Okay, now health claims, like what I said, is anything relating a nutrient to health. So that is called health claim. So, and those are the examples. There's table 3.6 in your chapter 3 in the book that lists a lot of them, the approved one. Do you know how we approve a certain health claim and it becomes approved, like an FDA approved claim? How does that work? How did we come up with calcium and osteoporosis, for example? Do you have any idea? Exactly. Years of human studies, not just animal studies. So years of research and always trying to get consistent results.
So does the FDA add them, or
The
does
FDA.
someone petition the FDA? saying,
Petition.
"Have this back"?
So there will be a petition. So, and then or sometimes the FDA funds research to figure out if we can validate a particular claim. Yes. Yes, Gray.
So what if they make a nutrition plan, and following that, they make a health claim to deal with it?
You mean nutrient claim?
Yeah.
They can do both. So you can have a nutrient content claim and you can have a health claim, both. But they're not interchangeable and they're not the same. We already did the lab. So moving on to chapter 4. Evaluation of analytical data. You'll be doing that the entirety of the semester. So we're going to talk about it. I'm sure you've learned about it multiple times, starting with high school. So it's just a refresher, and we relate it to what we do in food analysis. Okay. Let's see what you remember. Again, answering will get you your participation. Nobody's going to shame you if your answer is wrong. You're here to learn. Okay, let's look at that. And if you have an answer, share it. Caleb. Hey. Hey. Molly, what were you going to say? You were going to say A as well. So Millie. C? C? You're saying C? Okay. Any other answers? Tyler?
I was thinking B.
A and C? D? Well, how can they're contradicting each other? Wait a second. A and C, you said? Oh, okay. So A and C. Who says A? All right, so it's A. Okay. C has to do with accuracy, not precision. Okay, which is fine. But we're going to learn about accuracy and precision and what do we calculate to determine precision and what do we calculate to determine accuracy. Okay. All right, so anytime you do an experiment, you have to replicate. Why do we replicate? Any idea? Those of you that go ahead. Alicia. Oh, yeah. Yeah, yeah.
What if it has a lower standard, but it's not around that? Is it still considered precise?
Doesn't matter. Your results can be precise. Every time you run the assay, you get similar results with low variation among your replication. But it doesn't mean that your value is close to the true value. So the method can be precise, it doesn't have to be accurate. So I'll give you an example. So in our lab, we measure protein content, and we're going to learn in this class protein content. We measure protein content in complex matrices based on nitrogen, and we do two methods: DUMAS based on nitrogen combustion, and CalDAR based on protein digestion. These two methods will give you the most accurate for crude protein. Okay, if I want to measure protein in any product, complex, has fiber, has fat, has sugars, using an assay called BCA, bicyclinic acid. So it is based on absorption and reducing power. So if you have any reducing sugar in your sample, you're not going to get an accurate result. But every time you run the assay, you're going to get similar values, but not accurate. Right? Is it clear?
Yeah.
Okay, thank you. Good. Always ask. I mean, it's really help others as well to understand the concept. Okay. We always do replication. Always, always, always. And whenever, the longer the method steps, the more steps you have and more transfers, the more replications you should do, because there are more chances of error. Okay. So we always have to replicate, because doing one replication might not be an indication if you did it right, if it is accurate enough. So you have to replicate. So input analysis, every time we have an assay, we're going to tell you, okay, this we're going to run in duplicate, this is going to run in triplicate, this is we're going to do it 6 times. We're going to tell you, and then how do you report the result? You report it as mean, an average of all your replication. Now there are instances where median makes sense, but not in this the type of data we collect. So median is basically if you have 15 values, the median is probably number 8. Okay, so the midpoint of all the values. So it might be important for class grades. When I give you back your grades, I give you the average, the median, to see where half the class got this much higher and this much lower. It might make sense. But for the data that we collect and for the analysis, you will calculate mean. And then we want to determine the reliability of the assay. So accuracy and precision. When we're going to do a lab, let's say fat analysis, we're going to determine fat content using 2 official methods of analysis. For different food products, one method will be more accurate than another method. So you're going to compare methods and determine, okay, for high fat foods, I better use Soxhlet. For low fat, high carbohydrate, I better use Modina. The data is going to tell you that based on the accuracy and precision. So we determine accuracy and precision, and we're going to talk about how we calculate accuracy and precision. We take into account experimental error, systemic error. We're going to talk about all types of blunders even. So we're going to talk about all potential errors that will impact both accuracy and precision. Sometimes errors like systematic will impact accuracy, but not precision, because the balance is not calibrated. It's always giving you the same particular wrong weight. So your precision will be great, but your accuracy is bad. So some errors cause certain differences in accuracy and precision. Specificity, so how specific your method is for what you're trying to analyze, how general the method is, how specific for the component. Sensitivity and detection limit, they're two different things. We'll talk about them later, detection limit, or sometimes you hear the word threshold. So sensitivity and threshold are two different things we're going to talk about. Curve fitting, we're going to do a lot of curve fitting in fit analysis, having calibration curves. So we're measuring glucose. We need to use glucose standard and plot. Doing caffeine, we're going to have a standard curve. Doing calcium or iron determination, we're going to plot a standard curve. So linear regression is mostly, there are different types of regression, but in this class, the data that we collect mostly fit linear regression. So we look at correlation coefficient, which tell us how well the data fits a straight line. And then there will be also the R squared, which we call it determination coefficient. They don't want to come in? Huh? No, not in our class. It's okay. So we'll talk about linear regression in also later on. Reporting results. You know, what frustrates me sometimes is when students report data in a table and they have 10 decimal points. So why do we put all these decimal points? This is Owen, right? Okay. Why do we put all of these decimal points? What does it mean to us, all of these decimal points? So we're going to learn about significant figures and how many significant figures we're supposed to report. Excuse me. All right. So rejecting data. Sometimes you have 3 replications or 4, like for caffeine in lab, you have 4 reps. 3 of those replications are really close to each other, and 1 is just double or half as much. And you go, if you include that 4th one, it's going to damage your precision calculation. It's going to damage your accuracy. So we want to throw it out, but it's not like by eyeballing it. Okay, let's throw it out. There is a calculation that you can do to reject a data. So we're going to talk about that as well. Okay, so let's do some practice for +2 extra credit. Pull out a piece of paper and let's do some calculations. Put your name on the piece of paper.
Yeah. No one believes you. That's all I was doing.
Yeah.
All right, please put that on. Excuse me.
All right, so you are determining the moisture content of a sample, which seems to have really high moisture content. And you did 5 replications and you collected data, 5 different points. So calculate the mean, calculate the median, or determine the median. When you have an answer, raise your hand. You have an answer already. Okay.
82.56.
Yep. Yes, Rob. The median is 82.63. So basically the midpoint. If you have even number, if you have 6 replications, how do you get the median? Do you know? Go ahead. Emmeline. Exactly. Add the two middle points. So 0.3 and 4, if you have 6 points, and then divide it by 2, you'll get your median. Okay, so I know all of you know how to determine the average. So it's just an exercise. We're going to use Excel sheet next week in lab. You will use your Excel sheet to determine the average. So you won't be doing it by hand, but it's just a practice. All right. Which of these have good precision? A, B, C, or D? Go ahead, Sam. A and B, they both have good precision. All the data points are close to each other. Which of these have bad precision? Go ahead, Owen. Yes, they're very scattered. All right, which of these have good accuracy? Go ahead. B, only B. Go ahead, D, yes. Although they're scattered, when you look at them and you take the average, it will be around that bullseye in the middle. Okay. So which of these have bad accuracy? Go ahead, Razi.
A and C.
A and C. Which one has bad both? C. Yep. All right. So you get it. It's simple. All right. All right. So accuracy, accurate, close to the true value. So determine accuracy, we calculate absolute, and we calculate from the absolute, we calculate the relative error and multiply by 100. So the absolute error, you take your mean of the data, the X with the bar on top. That's your mean, and then you subtract the true value. Now, you will report it in absolute value. And sometimes the value is negative, sometimes it's positive, depending if your average is higher or lower than the true value. So that's why we call it absolute. So you just determine it without the sign. Where do we get the true value? How do you know what the true value is? You're determining moisture content of milk. Cow's milk. Haley, a reference, what kind of reference you would usually get? Sorry, I didn't hear you. So reference from?
Like a credible source.
A credible source. So USDA reference. So the USDA have a list of the composition of certain food or products. So when we give you products for your proximate analysis in a few weeks, we're going to give you products that you can find the true value either in a USDA source or on the nutrition label. We're going to trust that the nutrition label is correct. Okay, so if you're determining crude protein or crude fat, we look at the label, we'll see if your values are close to that true value, and then your absolute error will be your average minus what you see on the label or what is on the USDA. Because sometimes you don't, not sometimes, you don't have ash content on the label. So you wouldn't know what the ash content is of your product. So you go to the USDA website. So we will guide you, tell you where to find the true value. And then the relative error makes more sense to us because then you take the relative to the true value. So the difference by the true value, and then you multiply by 100. If you have percent relative error less than 10%, you consider this good accuracy. It's kind of like rule of thumb, kind of. If you have less than 10%, good accuracy, less than 5%, excellent accuracy. the smaller the percentage, the better the accuracy, obviously. If you have 50% relative error, it's like, no, this is really bad. All right, so let's practice. Mechanical pipette, you're going to be using them next week. Just a refresher, some of you have used them in the past, but we're going to learn again how to use them. And we're going to measure the weight of 1 milliliter multiple times, 3 times and 6 times. So you collected the data and you converted it to milliliters. How do we convert mass to weight to volume? What do you need? We need the density. So in your book, there will be the density of water based on the temperature of water, because density is impacted by the temperature. So you get the density, you get the weight, you multiply it by the density to get the milliliters. Okay, so calculate mean. What is the true value in this case? 1, exactly. If it's calibrated, you should be dispensing 1 ml. Or you divide by the density of the house and mix it up. Do you have the value for the mean? Anybody? Go ahead, Tina. Say that again for the mean. 9961. You want to maintain same number of significant figures. Okay. True value is 1 ml. What's the absolute error? Did you get it? What is it, Rob?
0.0039.
Very good. The relative error? Same. And then the percent relative error? 0.39. So it's very good accuracy. Okay. Standard deviation. You'll also use the Excel sheet to determine standard deviation in the lab, but you also need to know the equation, because sometimes in a quiz, you will have to calculate standard deviation, but I'm not going to give you 10 replication. It will be probably 3 replication. So it will be very easy to calculate. So standard deviation is the summation of any particular data point, subtract the average from that and square root of it. N minus 1, N is number of replications. So if you have 3, it will be 2 there. And then the square root of that. Okay. First, standard deviation. Sometimes, and I'll give you an example right just now, standard deviation is not enough or not correct to use to determine precision. And I'll show you an example when standard deviation means nothing in terms of precision. We have to determine coefficient of variation that takes into account the size of your mean. And that is important when you're comparing the precision among data sets that have different averages, different sizes of the mean. So we have to look at coefficient of variation. And I'll tell you in lab when you need to you calculate coefficient of variation when it is relevant. And we're going to use it a lot throughout the semester. For example, for caffeine determination, you'll be looking at caffeine in beverages that are high in caffeine and in beverages that are really low in caffeine. And if you want to compare the precision, you really have to look at the coefficient of variation. And I'll give you an example to think about here in a minute. So let's say you are measuring protein content by method X, in this case, NIR, near infrared spectroscopy. And then you're measuring in a flour sample, and you're measuring protein content in a protein ingredient, an isolate, which has really high protein content, so 92%. Much higher, almost like 9 times as much as the 12%. So one had a 1.2 standard deviation and one had 2.76 standard deviation. So which method is more precise? Okay,
The one with the lowest standard deviation.
the one with the lower standard deviation. Do you all agree? Caleb?
I think it's the second one because it's a much larger.
Yes, let's calculate coefficient of variation. So the first one, you have 1.2 standard deviation. So we need to correct, so coefficient of variation equals standard deviation relative to the mean. So you're correcting for the size of the mean times 100. So what is the one for NIR, the first method? So do the math for me, please. 1.2 divided by 12, is it 0.1? Yeah, so 0.1, that means 10%. Very good. So now the other one, the CV for the method, do math. Then we have, what's the standard deviation divided by the mean? So it's 2 point, what was it, 76? Divided by 92% times 100. What is your CV here? 3.2. There you go. Now, which one has better precision? So that's where coefficient of variation plays a big role, and we'll point it out to you in all future labs. So who's coming? Who really, really wants to be here?
That's.
We still have 10 minutes. Okay. All right. Well, you guys, if I get carried away, you can raise your hand and say, time's up, Pam. Okay. All right. So do you see the point here? And in future experiment, we'll be comparing caffeine in different beverages. We'll be comparing protein content in different food products. And some methods would be highly precise for a type of food and be low precision for another type of food. So that's why CV is important. If we have similar mean, like similar range of mean, then standard deviation is sufficient for precision. Yes, great.
If you only have like one.
Huh?
If you have two here in parent. If you only have one, you're saying that lower is better?
So if you have, okay, that's a good question actually from Greg. So if you just have this one, the NIR, and I ask you a question, is this method precise? How would you determine that if you're just looking at just one average? So you really need to calculate, and then you get 10%. Nah, it's okay, it's good, but less than 10 would be better. Less than 5 is excellent.
And the method vary for the thing you put through the Spectroscopy, spectroscopy machine.
Yeah, so different not texture, composition of the food might be suitable or not for NIR.
And that would change the version variation.
Exactly, exactly. The type of food really impact whether the method is suitable for it or not just NIR, anything. Yeah, so this is good. So Grace's question is really important for you to know when in an exam, if I just give you the value of the flour and I just tell you, is NIR precise in this case? How would you know if you don't calculate CV? Because you don't know 1.2 standard deviation and you have an average of 12, you really need to calculate. But if I tell you compare which is more precise, it doesn't matter. This might be 20% and this might be 10. Which is more precise? This one, the one that has lower, although both of them are not great, but if I'm asking you to compare, so you would need to calculate for both. Okay, does that make sense to you guys? Great. Okay. Now, confidence limit or interval, it just gives you the range of your data. Okay. And in order to calculate, you want the relative error. So T for the T value times standard deviation over the root of number of replication, N is for number of replication. That is your standard error. And then your confidence limit is your average plus or minus your standard error. So it gives you the range of the data. So the narrower that, the more likely your values are, fit within the expected value. So the narrower range, the better, basically, for the confidence interval. Now, depending on your number of replication N, you either will need to use Z values, but if your values are less than 25, if your replication is less than 25, you use T value. So in your book, page 40, you have a table for Z value and a table for T values. So the way you look at them, well, let me look in the book. Page 47. Page 40, sorry. So table 4.2 gives you the Z value. So degrees of certainty, if you want 90% confidence or 95% confidence, I would tell you, I want 95% confidence, your Z value will be 1.96. For anything that is more than 25 replication. So for larger number of replication, at 95% confidence, your Z value will be 1.95. For T values, on page 41, so here you really need the degrees of freedom, which is replication -1. And then you have levels of certainty or confidence. So 95, 99, 99.9. I would usually in our world, we tend to go with 95% confidence or an alpha of 0.05. So depending on number of replication, you subtract 1 and then you look for the T value. Let's say you have 6 replication, like an example for next week's lab. You would go for degrees of freedom of 5. If I tell you 95% confidence or alpha of 0.05, your T value will be 2.57. Okay. Let's calculate standard deviation, coefficient of variation, confidence interval. Huh. Okay, what's the standard deviation? Go ahead. 0.0019, yes. And the CV? Since the true value is 1, you just take that and multiply by 100. Would be 0.19. Anybody got to the confidence interval? Okay, let me tell you the t-value here for 3 samples. 3 sample degrees of freedom. 4.3 is the t-value in this case. Do you have it, Tyler? No. All right, anybody? Go ahead.
I got 0.99.
What did, oh, one number? Or you got a range?
It's okay.
So you can report it as a range, or you can report it as a mean plus or minus your relative, your standard error. So either way is fine. You can have it as a range. Or like that. Okay. Good. I will stop here for today. No, I don't think I. No. I didn't get near anybody today. Okay. Alrighty. Thank you. I'll see you on Friday. Give your sheet of paper to one of our wonderful TAs. Huh?
What was the paper for?
Didn't you write everything down?
Oh, I didn't understand. I just heard write your name on a piece of paper.
And solve all
Wrote
the
it down,
questions.
wrote all my notes down.
Did you solve anything?
Yeah.
You had them written? Okay. Just write your name on that piece of paper and give it to them.
Now I understand.
Yeah. Huh.